Well, alright, so we've had a couple snow days here, so I need to do a video to get you guys caught up. So please take notes throughout this video. You're going to need it to do a project that I have you working on. Okay. So write down this I can statement. I can determine if a molecule is polar or nonpolar based on its symmetry. Don't worry, you're fine. Alright, so you already know how to tell if a bond is polar or nonpolar based on the differences in electronegativity, but that's just for a bond, not for a molecule. Okay? It's a little bit different. Okay? Knowing if you have a polar bond is the first step of knowing if you have a polar molecule. Okay? So what I want to do, first of all, is let's put a definition of what it means to have a polar molecule, and there's a key term I got to show you for this. Alright, if we're talking about a polar molecule, we're saying that in our molecule, one end, and in parentheses, I'm going to use this word pole here, and it's just like North Pole or South Pole. Okay, it's just one end of your molecule. One pole of the molecule is partially negative and the other pole or end is partially positive. Key thing here, opposite poles have opposite partial charges. Okay? That's what's going to be a polar molecule. And when you have a polar molecule where you have opposite poles having opposite partial charges, it is said to have what's called a dipole. Okay? All a dipole is a molecule that has one end is partially positive and the other end is partially negative. It is said to have a dipole. Okay. Alright, so let's get into this. The polarity of the molecule is going to depend on two things. Alright. First of all, you have to have a polar bond in order to have a polar molecule. At least one bond in your molecule must be polar. If none of your bonds are polar, then you're going to have a nonpolar molecule. That's easy enough. The tricky thing is you can have polar bonds, but your molecule will end up being nonpolar because it does not have a dipole. Right? And here's what you need in order for that to happen. The molecule needs to be non-symmetrical, is the way I phrase it. Because if it's symmetrical, what's going to happen is the polar bonds will in effect cancel each other out. So let's add this, or the polar bonds, no parentheses here, I think of it as they cancel each other. And with some examples and some models, I'll show you what that means. Right. What I want to do is I want to get into a couple examples of polar molecules. So I'm going to slide this up. We're going to look at water H2O and ammonia NH3 and see why they're polar. Okay. And here's the thing, it has to do with the fact that there are not any, that there are unshared electrons around your center atom, and it bends these things. Okay, you'll see what I mean here. You know how to get to this right here. You do your dots, figure out that you have to bend those two hydrogens down to get your shape. Okay? And water has that geometry right there. It's bent. Now the next thing is let's take a look at our bonds that are in this molecule. Is a bond between hydrogen and oxygen polar? And if you subtract the two electronegativities, you're going to find that it is a polar bond. Okay? And the partially positive end is going to be by your hydrogen. And so what we did to show it is you drew an arrow off that going toward your partially negative oxygen. Okay? And that happens in each one of these bonds. So draw it twice so we can see what happens here. Like that. Right? So now, we have a polar bond. Do we have a polar molecule? Do we have a dipole? And here's the thing we do. Because, take a look up at the top. Your top pole is partially negative. Your bottom pole is partially positive. Okay, so you have a dipole. That's a polar molecule. Partially negative pole on top, partially positive pole on the bottom. Okay, polar molecule. Same thing here, NH3. NH3, if you do its dots and then you draw its shape, you see that those unshared electrons force those hydrogens into a pyramidal shape that's like that. It's called a trigonal pyramid. Right? And so now you look at the bonds between hydrogen and nitrogen, and you will see that in fact it's a polar bond. Once again, hydrogen is more positive. Okay? And the more negative is your nitrogen. Okay? And here's the thing, each one of those three bonds, that's what it does. Okay? Your electrons that are being shared spend a lot more time by the nitrogen than they do the hydrogen. So if you take a look, same thing here. The top pole is partially negative. Same thing. Bottom of your molecule, partially positive. We have a dipole. It is a polar molecule. Now to me that's not too hard to see. Seeing them cancel out might be a little bit trickier. So let's do two more examples here. We'll do carbon tetrachloride and we'll do CO2. Okay, these will both end up being nonpolar. I'm going to ruin the surprise already. Let me get situated. Alright, so we have here carbon with 4 chlorines around it, so you should know it's a tetrahedral. You should draw it like that. Right. If you look at your electronegativities between carbon and chlorine, carbon is the one that's more positive, so the chlorine is going to be the one that's more negative. So each one of these bonds, the arrows would go like that. Okay. And so now look what happens to your opposite poles of your molecule. They have the same charge. Your top pole, partially negative. Bottom pole, partially negative. Okay. No dipole. In order to have a dipole, the opposite poles have to have opposite charges. Alright, last example here before I show you some models. CO2. Carbon's in the middle. Your two oxygens out the outside. They don't bend down. They're straight. It's a linear molecule. Right. You need to know how to get there. Right. And it's all because no unshared electrons around your center carbon. Okay. It's very important you know how to do that. And now let's take a look at the bond between carbon and oxygen. Alright, it's also a polar bond, and the electrons spend more time around the oxygens that have the higher electronegativity. So your carbon is partially positive between each one of these bonds, and your arrows point out towards your oxygens that will be partially negative. Okay. And take a look at your opposite ends here. This end here, what partial charge? Well, it's partial negative. This end here, what's your partial charge? Oh, the opposite end, also partial negative. So guess what? No dipole. Alright, they are both non-polar molecules. Bam, easy as that. Alright, now I got some models that I want to show you.
Well, hello beautiful people, how are you doing? I told you I would show you some models to maybe sort of illustrate the difference between a polar molecule and a non-polar molecule. And I want to start out by showing you the difference between the molecule water and carbon dioxide, CO2. Because we said water was a polar molecule that has polar bonds. CO2 is a non-polar molecule, but it has polar bonds. So to try and explain it to me, looking at a model is the big thing. And the way I think about it is you have a top and bottom to a molecule, and they have to have opposite partial charges. And it doesn't have to be top and bottom. It can be any direction you want to think of, if you want to think of right or left too. But opposite poles of your molecule better have opposite charges. Okay, so here's the thing. CO2, because that center carbon doesn't have unshared electrons, it becomes linear. You know how to do that right there. And you really only have opposite ends of the molecule being your two oxygens. Okay, and if you look at your notes there, we said the oxygens are both partially negative. So you have a partially negative end up here, a partially negative end down here. They cancel each other out, those polar bonds do. So your total molecule is considered to be nonpolar. Does not have a dipole. Your H2O, on the other hand, you could say, well, now the top and bottoms, okay, are the same. We got partially positive here and partially positive here by our two hydrogens, okay? But if you look at it this way, okay, when you orient it this way, you have a top here that's partially negative and a bottom here that's partially positive. Okay? We have opposite poles have opposite charges, so it's said to have a dipole, so this would be polar. So knowing how to do the shapes is very important. Okay? If water was not bent, okay, it would end up canceling each other out with our polar bonds, just like CO2 does, and water would be nonpolar, and life as we know it would cease to exist. Okay? So don't note the difference here, the bending, making this molecule not quite so symmetrical is what does that. Right? I want to show you NH3 here. NH3, if you consider this black ball the nitrogen and our three yellow balls the hydrogens, you have a bottom pole of your molecule, the yellow here, they're partially positive, our nitrogen being partially negative. Opposite ends of your molecule have opposite charges. Okay? You have a polar molecule. Compare that to carbon tetrachloride. Okay? We got the chlorines around the outside. Okay? The electrons hang out there more because they like the chlorine better. Okay? So notice here, this end of my molecule is partially negative. The bottom end of my molecule is partially negative. And the key thing here, this is perfectly symmetrical, no matter which way you turn it. Okay. It looks the same, and your opposite ends end up having the same partially negative charge. Okay? Much different than when you try and rotate NH3. Okay? This here looks different here. Okay? It's not perfectly symmetrical. And I'll do one more example here. If you had, let's say, boron trichloride, okay, the blue ball here in the middle is your boron, and your purple ones are your chlorines. The chlorines would be more negative, so your top here, partially negative, bottom here, partially negative. No matter which way you rotate it, okay, you're going to see that it's going to be the opposite poles of your molecule have the same partial charge. So this one right here, no dipole, nonpolar molecule. It has everything to do with the symmetry of this molecule as opposed to the symmetry of your NH3. Okay?